Hello everyone, I am Alok Kumar, a senior mathematics faculty at Sri Chaitanya IT Academy, Hyderabad. It is going to be my third and final lecture on limits. While planning the lectures, I had taken care to make them sort of independent of each other so that the new viewers that join us today should have no difficulty in following the contents. So let us now go to the lesson. I'll share the screen and here we go. Okay, so today I will start with some very instructive examples, not to be confused with simple examples, that will build an entire sort of techniques and then we can apply them. So my first example would be that suppose we take limit x tend to 0 cos of pi by 2 cos of x over sine of x. Although the problem is not difficult, but still some things stand out. I would try to give you motivation also so that you can learn that how to use the technique that we are teaching. So cos of pi by 2 cos x is there. Now, the moment you see something like that, you know that sine of t upon t, limit t tend to 0, it's something good. That's one. So is it that we can change this cos to sine? We can. In fact, we know that cos of theta is sine of pi by 2 minus theta. So I can write this as limit of x tend to 0 sine of pi by 2 minus pi by 2 cos x and whole upon sine of sine x. So that gives me limit of x tend to 0 sine of pi by 2 minus pi by 2 cos x. So I can take pi by 2 common. I am left with 1 minus cos of x whole upon sine of sine x. Next step can be that because we are writing this kind of thing, we'll write limit x tend to 0. Now using 1 minus cos t is twice sine square t over 2. I simplify a bit. So I'll write this as sine of pi and sine square of x upon 2 and sine of sine x. So the person who is watching it closely, he or she must have discovered that right now we have not really taken limit. We have just set the stage for further preparation. So we are reducing our given expression in a form such that I can make use of known identities or known special limits. Because sine of argument of sine is pi sine square x by 2, this argument that tends to 0, this argument also tends to 0, something that we need when we apply limit of t tends to 0 sine t over t equal 1. These are satisfied now, so we can go forward and we can just adjust things now. So I write limit x tend to 0, this is sine of, and this is pi of sine square of x over 2 upon pi sine square of x over 2. These are mere adjustments because I need 1, 1, 1. Now this is pi sine square of x upon 2 times 1 upon sine of sine x over sine x times 1 upon sine x. So I have just written sine t by t, here sine u by u, and the excess is adjusted here like 1 over sine x, and this is pi times sine square of x upon 2. So far so good. Now this leaves you for good. This whole thing this whole thing becomes 1 when you take the limit. This whole thing becomes 1. So we stop worrying about these things. Now we have left with pi sine square x over 2 and sine x. So I can write now pi times sine of x over 2 upon x over 2 whole square in a bit to adjust and get 1. So that leaves me with x squared over 4 and 1 upon this is sine of x over x and times 1 upon x. Again, this all thing become 1 each. This limit give you 1. This also give you 1. This x cancels with x squared, giving x in the numerator. And so now when you take limit x tend to 0 of the whole expression, only lot of ones remain and pi, and the final term is this x that becomes 0, and so your answer becomes 0, which I have boxed. So it was a simple problem, but we learned here that when you see cos of something, cos or even sine also, you try to adjust and write in terms of sine so that this argument t, this tends to 0. That's what the takeaway from this example is. Okay, so let's go to the next one. We have to evaluate limit of x tend to 1 n times x to the power n plus 1 minus n plus 1 x to the power n plus 1 over x minus 1 whole square. We will use this example in our next problem also. So let's follow it. So they are both polynomials, polynomial of degree n plus 1, and this is degree 2. Now this tells you that we expect that the numerator, which is n times x to the n plus 1 minus n plus 1 times x to the n plus 1, we expect that this we can write as x minus 1 square and times some expression. And then we can take limit because this x minus 1 whole square will cancel from both numerator and denominator, and we will be evaluating some other expression. So let's try to do it two ways. So this is the first solution. In first solution, I will be like doing that. So let me just insert some pages and okay, so let me insert a couple of pages more because I may require it later. Okay, we are here. Sorry about that. Now limit of this, I have to write again because this has gone down. So we were doing this kind of thing that this was okay. So it was limit of x tend to 0 and n times x of n plus 1 minus n plus 1 times x to the n plus 1 and plus 1 upon x minus 1 whole square. Now, as I told you that I expect to pull out some factor of x minus 1 square from numerator. So my first solution will be based on simple factor. Just we'll factor them. So we'll arrange our work like that nx n plus 1 n x to the power n plus 1 minus n plus 1 x to the power n plus 1 plus 1, that can be written as, we can just pair up this xn. So we'll write n x to the power n plus 1 minus n times x to the power n. This is n. So let me erase that. This is just simple n. So it should be erased here also. So now we can write nxn minus xn plus 1. If you take common n times x to the power n, we'll get x minus 1 minus, this is x to the power n minus 1. So this I can write as n x to the power n x minus 1 minus x minus 1, and then xn minus 1 plus xn minus 2 all the way till 1. So x minus 1 is common, and we are getting nxn minus xn minus 1 minus xn minus 2 all the way till 1. We can again pair off. So this n I will break up in n parts. So we'll use x to the power n minus xn minus 1 minus x to the power n minus xn minus 2. This is plus, and then again plus xn minus 3, and so on. The last term would be xn minus 1. Now we are almost ready. We know that each of these expressions contains x minus 1 as a factor. So I will take the limit of this now. So I'll write now limit of x tend to 1, x to the power n plus 1 was the expression n times x to the power n plus 1 minus n plus 1 x to the power n plus 1 and whole upon x minus 1 whole squared. This rewrites as limit x tend to 1. This is x minus 1 and times this big expression which I've underlined and times x minus 1 whole squared. So I'm left with limit of x tend to 1. 1x minus 1 cancels off, and then we have got xn minus 2 minus 1 plus, so this is 1, this is 1, and then xn minus 2 all the way till xn minus 1 and upon x minus 1. Now we will use everywhere limit of x tend to a, x to the power n minus a to the power n upon x minus a. It's again a standard limit, and that equals n times a to the power n minus 1. Using this one, I can write this one now because I can take common. This xn minus 1 is here common. You get x minus 1 upon x minus 1. Xn minus 2 is common. X squared minus 1 upon x minus 1. And last term is xn minus 1 upon x minus 1. If you apply this formula repeatedly and put the limit 1, this number gives you 1. This gives you 2 because this exponent is 2 all the way 3 until n. And so you get n times n plus 1 over 2. And that's my final answer. So we have found the limit of, let me go back and show you because there was some problem initially. So limit of n times x to the power n plus 1 minus n plus 1 times x to the power n plus 1 upon x minus 1 whole square. So my first solution is based on the factorization. Because x minus 1 squared appears in the denominator, we expect that they must appear at least as much in the numerator. So x minus 1 whole squared or degree or cube terms. But then when we factorize, we found that this contains exactly x minus 1 whole squared. So first was that combining these numbers appropriately. So we chose n to go with n, and the single one was left over here. And then following this method, we got the step 1 times this one. So x minus 1 already has come out. One more x minus 1 we need, and that of course will come out from here, because if you call it p of x, if you call it p of x, then you know that p of n, when you put the value p of n, p of 1 gives you 0 because n is n, and you get 1 1 1 n times, so they together make up n, and so p1 equals 0. There is reason to expect that x minus 1 is lurking over here. It will again come out. It does not disappoint. Now, once we know this is a factor, now we are using the basic limit. So limit x tend to 1, we are almost ready to take limit. So limit x minus 1, and then we write in this form. And here we take it term by term by taking common. And when you have got common, this xn minus 1 upon this one, you are seeing that you will get first term as 1, second term as 2, because this keeps on changing the power 1 2 3 till n. So your final answer is nn plus 1 over 2. So that's your final answer. Let me quickly use it to solve a problem which makes use of it and some other concepts. So you have to find limit x tend to 1, 100 times x to the power 101 minus 101 times x to the power 100 plus 1 whole over e to the power x minus e and sine of pi x. Of course, the numerator looks familiar. We just met it. But the denominator has got some terms like e and sine. So it looks like trigonometric, algebraic, exponential, all functions are mixed up. But don't worry, we'll cross our bridges one by one. Now, a piece of advice. When you see e to the power x minus 1, when it is a chapter on limit, and you happen to see e to the power x minus 1, then what's your reaction? When you see, say, sine of t, what's your reaction? I would answer like this, that when you see a term like this, it needs e to the power x minus 1 over x to be useful, because we know that this limit equals 1. When we see sine t, then we need sine t over t, so this again becomes 1. Everywhere x is tending to 0 or t is tending to 0. Similarly, when you see ln of 1 plus x tend to 0, it needs ln of 1 plus x over x, so that this is a good thing called 1. So these are the suggestions that you have to think of when you come across these patterns. Now this is e to the power x minus 1, and x is not 0, 10 to 1. That's a cosmetic change. So I can write this as e times e to the power x minus 1 minus 1. Just like last example, remember the first example that we started the class with, cos of something like pi over 2 times cos x. We loved from go to cos to sine. Here still sine is there, but this sine is there, sine pi x. But when x tends to 1, this does not tend to 0. This tends to 1, pi. So that spoils our game. We don't want this. And so I will use sine of theta as sine of pi minus theta. And I can write this as sine of pi minus pi x. Now we are good, because this expression, this argument of sine, as x tends to 1, indeed tends to, this tends to 0 as x tends to 1. So we are okay. Similarly, this exponent tends to 0 as x tends to 1. So which we want like this, e to the power x minus 1, the top, the exponent must tend to 0. The argument of sine must tend to 0 to make use of these formulae. Next, we simplify a bit. So we'll write now equal to limit of x tend to 1. Numerator, I will just write using n times xn plus 1 minus n plus 1 times xn and plus 1. And for a moment, we put n equal to 100. There is no point in carrying this number 100. There may be a bigger number. So let's focus on the work. In the end, when we get the answer, we can, of course, again plug in our values, that n and whatsoever. So now this is this, and it was e to the power x minus x, e to the power x minus e, and sine of pi x. So rather I will raise them and I will do what I wrote. So already we have done the work, the good work, that we have taken out e and wrote e to the power x minus 1 minus 1. And for some reason that I told you, we chose to write sine of pi minus pi x. We are almost there. Now, this needs, right, you got it right, x minus 1, because it needs this one. It will leave you for good. Here, this is sine of pi times 1 minus x. It needs pi times 1 minus x. But these were not there. So, in fact, you have got minus pi times x minus 1 whole squared, because that was not here. So now, when I take limit, this whole thing becomes 1. This whole thing becomes 1. We are happy with it. So it means that I want to find now minus 1 over e pi, that is common, that I can take out, and limit of x tend to 1 n times x to the n plus 1 minus n plus 1 times x to the n plus 1 over x minus 1 whole square. And this is exactly the problem. This is exactly the problem that we just did. This one, this answer was n plus 1 over 2. So your final answer, as n is 100, that becomes minus 1 over e pi times 101 over 2. That is 50 over e pi. Don't forget negative sign. And so your final answer would be minus 5050 upon e pi. Just notice how cleverly we manipulated. So it was first we did this kind of thing, that so let me go back and show you what we really accomplished. So the problem was given to be this one, limit of this whole thing was there. So I noticed, first of all, lot of terms, some trigonometric, some exponential, and some algebraic. We will deal them one by one. So we got first e to the power x minus 1 minus 1 by taking e common, because we want the exponent of e to tend to 0. Then only I can do anything about it. Remember, e to the power t minus 1 over t tends to 1, or limit equals 1 if t tends to 0. If t is not 0, it's not a limit problem. You can evaluate directly. Similarly, sine pi x, this inside this pi x, you would have loved to go it to 0, which it does not. It is in fact pi. We have got to play around with it by using sine of theta, each sine of pi minus theta. So I wrote sine of pi minus pi x, which has the advantage of making this limit tend to 0. Now we are all set. So we will calculate, give it x minus 1, give this fellow pi 1 minus x. And so the next stage was just setting your house in order. So you were just writing e to the power x minus 1 upon x minus 1 and sine of pi minus pi x over pi times 1 minus x. And the excess you multiplied, that was negative of pi x minus 1 whole square. That's little algebra. And finally, you came up with this circle part in this one, in red ink. And that number, that expression, we already know from the previous example, that was n times n plus 1 over 2. Finally, plug n equal to 100. And there you go. Your answer is 5050 upon e pi and negative of that. Okay. Let me change color for a while so that we can keep track. Limit x tend to 0, e to the power x minus ln of x plus e. That looks strange. And upon e to the power x minus 1. Again, the theme that I've been telling you repeatedly is look for q's. So e to the power x, if e to the power x is there, you badly want negative of 1. And then you want x also. First you want this, e to the power x means minus 1 you want. If it is ln of something, you want ln of 1 plus t, where t tend to 0. This also same, x tend to 0. This is what you would love to have. It is not given, so let's see if I can arrange my work. It turns out I can. Limit x tend to 0, e to the power x minus ln. I take something common. I take common e, that gives me 1 plus x over e. That's fine. So I'm writing x plus e is e times 1 plus x over e. So this number x over e, when x tend to 0, will tend to 0. So that serves us good. Ex minus 1. And now play with the rules of logarithms. So ln of ab is nothing but ln of a plus ln of b. This little formula we use here in the numerator, second term. And we get e to the power x minus ln of e minus ln of 1 plus x over e upon e to the power x minus 1. That is limit x tend to 0 of e to the power x minus this number is 1 and minus ln 1 plus x over e and upon e to the power x minus 1. The first term is quickly calculated. That is your 1. There is no limit. And minus limit x tend to 0 ln of 1 plus x over e upon e to the power x minus 1. Now remember, when you spot ln 1 plus t, you give it t. It will leave you. If you spot e to the power x minus 1, give it x, all tending to 0. They will give you 1 each. So motivated by this, we write now, this one is okay, this negative is okay. So this is ln 1 plus x over e whole upon x over e. So we have given this number to it. So multiply by x over e, then e to the power x minus 1 over x. You have given it x, so multiply by x. And now it turns out that when you take the limit, everything cancels. This x cancels. The way arranged, this is 1 minus this limit becomes 1, this limit becomes 1, and so your answer becomes 1 minus 1 over e, and that's your final answer, 1 minus 1 over e. You must have noticed that how artfully, how skillfully we made use of basic limits, very basic limits, to arrive at our answer. Because it's the third lecture, so I am covering different techniques. So this is a more varied collection. Now the next one will tell you something about expansion. So we have got e to the power, let me change the color, and we can just go ahead, and this is okay. This is e to the power sin x minus 1 whole upon x square. We want limit x tend to 0. Now, the first thing to observe in these problems is don't go rushing for expansion. Expansion should come at a later stage. Don't expand sin x, no good. It's no good. So what we do, that we think of sin x as t. So if I have got et minus t minus 1, what would I love to have? In the same way that if we have et minus 1, e to the power t minus 1, I would love to have a t, so that it will give you 1. It so turns out that et minus t minus 1, we need to have t squared. This needs t squared, so that it's get evaluated, and it's a good guy, it then leaves you, and then you focus on the other part. So in a bid to make this, I will write limit x tend to 0 and e to the power sin x minus 1 over sin square x. I have added from my side, and this is sin square x over x square. So this number happens to be 1. This limit is not a problem, so this goes to be 1, And then we are left with limit x tend to 0 e to the power sine x minus 1 over sine square x. And as I remarked earlier, that the moment you see this, they almost jump at you. This sine x screams. It's like you put sine x is t or u, whatever you like. So sine x is u, I will go with u this time. So u, and then you are getting as x tend to 0, as x tend to 0 sine x, then u also tend to 0. So this reduces to limit u tend to 0 e to the power u minus 1 over u square. And next step is just expansion, the last thing. So we know e to the power u is 1 plus u over factorial 1 u square over factorial 2, and then u cube factorial 3, and all those numbers we don't need them. We need just till u square. So when you put that, limit u tend to 0, 1 plus u square factorial 2, and all those numbers, just write one more, u get factorial 3 minus u minus 1 upon u square. That gives you limit u tend to 0. You are getting u square over factorial 2 plus u cube factorial 3, and so on upon u square. And the last step is that you are writing this as 1 over factorial 2 plus u times 1 by factorial 3, and all these numbers. When u tend to 0, this tends to 0, and you are left with 1 by 2. So your final answer becomes 1 over 2. That's your final answer. So you noticed how we did not get terrified, or we did not get carried away by this sin x. Even if I remark now that even if this was, suppose the problem was e to the power sin x minus 1 upon x tan x, or e to the power sin x minus 1 upon x sin x, anything, they all are these, the problem this, the problem this, and the problem this, they all are equivalent, they're same problem. Because ultimately you need x square or sin x square, and this tan x behaves like x, this sin x behaves like x, and so we are done. We almost get the same expression, just some little changes there. Substance remains same, and you still get the answer as 1 over 2. Okay. Now I will take up 2-3 problems which will tell the limit in case of greatest integer function. And they will hinge on one property, they will all depend on one crucial property, that if t is element of R, and if floor of t, this is called floor of t sometime, or box of t. So this floor of t is of course defined as the greatest integer not greater than t. So we get this t less than or equal to t and greater than t minus 1. It means wherever t is there, you are just looking for the nearest integer. So this expression holds, that floor of t less than equal to t and t minus 1. This inequality, although basic, we will use it pretty much 2-3 places. So to begin with simple examples, I give you limit x tend to 0, x times 1 over x. This was other is limit x tend to 0, x over a times floor of b over x. Here a and b both are positive. And final example in this triology will be this x, floor x over x. So these 3 examples, which I name A, B, and C, these 3 are connected. So let's attempt A. That will tell you a problem which we will use right afterwards. That will be a little tougher. This is just basic. So what we do, that first realize that we need to use that. So we'll write 1 over x float less than or equal to 1 over x, and 1 over x minus 1. This is true even if x is positive, negative, whatever. But can we multiply by x? No. That depends on where x is positive or x is negative. So we'll take the cases now. We'll say if x is positive, then multiplying with x will preserve the sign. Sign won't change. So less than x times 1 over x box and x times 1 over x. So it means we have multiplied by x throughout. X is positive, so sign is preserved. And so we are left with 1 minus 1 over x less than x times 1 over x float less than equal to 1. Now, when you do this kind of thing, then you see what will happen. This is 1 minus not 1 by x. So let me just change this. This is 1 minus x. So I'm sorry about that. This is 1 minus x. Now, these are two expressions. When x tend to 0, this is anyway 1, and this also is 1. Left side is also 1. So there is a useful principle called sandwich theorem, or the other name is a squeeze play theorem. So there are two theorems, rather one theorem. There's two names. So the common name goes by sandwich theorem because it tells you some image of what the theorem really does. So this expression is sandwiched between two expressions f and g. So it tells you that if something is sandwiched between two expressions, and when the limit on the left side and right side are same, then that tells you that this expression itself has same limit. Or this is same as a squeeze play theorem, in the sense that we have a squeezed, you have a squeezed the expression x times float of 1 by x between these two expressions, 1 minus x and 1. So either way, the imagery is clear. And when you get this, then we can conclude from here that as this is a function, say ax less than equal to g of x and greater than fx, this fx also tends to L and this also tends to L. So a possibly cannot have any other limit than L, and indeed the theorem tells that a has limit L. So we know that in this case the answer is 1. But this is just the right hand limit because we have taken x positive. We have not dealt with x negative. We have taken x positive, and so we need to do some more work. So this x positive is done. Similarly, we can replicate for x negative now. So it's like if it is x is negative, argument remains same. The only thing is that till here we are fine. This step remains unchanged, that 1 over x minus 1. But now when you multiply by x, then because x is negative, these expressions, these signs will change. The sign will not be maintained, it will be reversed. So we get x times 1 over x minus 1 greater than x times floor of 1 over x greater than or equal to x times 1 over x. That gives you 1 minus 1 minus x greater than x times 1 over x greater than equal to 1. Nothing much has changed. Only these expressions have changed sides. Earlier one was here. Only this has changed sign. This inequality has changed sign. This is still limit is 1. This limit is 1. So by sandwich principle, we say sandwich theorem, it tells you that limit x tend to 0, x times 1 over x float, that is still 1. And so we know that this left hand limit and right hand limit both are 1 that we calculated. So your answer becomes that this both are 1. So we have ultimately that limit x tend to 0, x times 1 over x equals 1. Similarly, you can prove the other part that I have given you, that x by a times, just take it as a homework or just try your skill when you have time. Limit x tend to 0 and a be positive. By the exactly same set of argument, you should get this answer as b over a. We have done for a special case a equals 1, b equals 1, but a special case and general case are dealt in the same way. We are just multiplying, and a and b are given positive. At least a is given positive such that it will help you in multiplication, even b also. Okay, then I am taking up third because that that we cannot conclude by sandwich. This is x by x, limit x tend to 0. This you can't conclude by sandwich. So we will use this way now, that we'll calculate first right hand limit and then left hand limit. So I take x is 0 plus h tend to 0, but h is positive, so 0 plus. So this is truly right hand limit. So h 0 and h tend to positive, right, like this. Here I will take x is 0 minus h, and again h tend to 0, h is still positive, so that we are truly on the left side of 0. So this is 0, one left hand limit, one right hand limit. So we just write this further. So our limit becomes left hand, calculate right hand first. Right hand limit becomes limit of h tends to 0, floor of h, and upon x was 0 plus h, that is h. That is limit of h tends to 0. This floor of h, remember h is positive but very small. You can say 0 less than h less than a. It's very small, as small as you can think of. So that number, this floor of h, that becomes 0 and over h. And if this is the case, then your answer is 0. I am likely to issue a warning that this h, some of you might be wondering that maybe this h is also 0, so it's not a 0 by 0 or something. The answer is this, that h is of course tending to 0, but in limit we always say h is 0, h is tending to 0, but different from 0. Means you can go as close to 0 as possible, but not exactly at 0. You can never go at 0. So in fact, when you say limit x tend to a, it means that you can go to a approaching from left or right by being as close to a as possible, but not never at a. So h is never 0. We see h is positive also written. So h is never 0, and so it is 0 upon some finite number, and so this is 0. So right hand limit exists. Let's calculate left hand limit. For that I need limit still h tend to 0, h is positive. It is 0 minus h, so minus h floor and over h. So this over minus h, and this time we'll get limit of h tend to 0, floor of minus h. This is negative of 1 and negative of minus h. So that is limit h tend to 0, 1 over h. This limit does not exist, it blows up, like it just goes to infinity. So this limit does not exist, and so we will say that because left hand limit does not exist, right hand does. Overall, the limit does not exist because LHL does not exist. Let us use these ideas in a really tricky problem, much trickier. So we are using limit x tend to 0, x square, 1 plus 2 plus 3 till 1 upon modulus of x and floor part of that. This is floor of this. So 1 upon mod x, this crazy thing, this number, this one, because it is enclosed in a floor. So this whole number, this whole thing is an integer. And because it is mod of x, so it is positive integer, we can say positive, say it is 3, 4, 11, whatever can be, so it is integer n, call it n. So first thing to notice that first let me simplify it as much as possible so that we can prepare the stage for applying principles of limit. That's true of any problem, that first we are setting up the stage, we are trying to simplify as much as possible, and then apply the relevant properties of limits. So I will reduce this using 1 plus 2 plus 3 plus n as n times n plus 1 over 2. That's the first step. So I write limit x tend to 0, x squared. It's a huge expression, use lot of space. So this is 1 over mod x and floor part, that is your n. Use a bracket. I need n plus 1. So 1 over modulus x floor plus 1. So n plus 1 has come over 2. So almost we are okay now that we have used some expression. Now let me simplify this and keep it in your view so that you can check. So again we are using floor of t less than or equal to t and greater than t minus 1. So I'll write some inequalities. First is this floor of natural inequalities, floor of 1 upon mod x less than equal to 1 upon mod x less than 1 upon mod x minus 1, that is 1. This is 1. And the next one, I can just add 1 to both sides. So I will write 1 upon mod x floor and plus 1 less than equal to 1 over mod x plus 1. Adding does not change any sign. 1 by mod x minus 1 plus 1. So that cancels. So we get 1 over mod x. Now the moment we got this thing, we can think of multiplying these two. We can multiply a star and double star, these inequalities, because things are all positive, because x tend to 0. Now, when you multiply, you get 1 upon modulus x minus 1 times 1 upon modulus x less than 1 upon modulus x floored times, I'll use a bracket, 1 upon modulus x floored and plus 1 less than or equal to 1 upon modulus x times 1 upon modulus x plus 1. Now, our thing is to multiply by x squared. The original expression is given to be limit this one, x squared times this whole thing, limit x squared. So multiply by x squared whole side and divide by 2. So you will end up with x squared times x squared by 2 times 1 by x modulus and floor of that, and times 1 over modulus x and floor of that, and plus 1 less than or equal to x squared over 2 times 1 upon mod x and 1 plus mod x upon mod x, and this side you will get 1 minus mod x upon modulus x whole square, and multiply both sides by x squared by 2. As we know that x squared is modulus x whole square, this rewrites as half times 1 minus modulus x less than this big expression, which limit you want, and this is half times 1 plus modulus x. Again, sandwich theorem comes to our rescue, and we find that in fact these limits, we find that in fact this one and this one, they both tend to 1 over 2 as x tend to 0. And so this expression is sandwiched between these two, and we can conclude that original limit x tend to 0, x squared times 1 plus 2 plus 3 plus 1 over mod x floor part, this limit is nothing but 1 over 2. This is a beautiful problem. You understand how we have used simple things in quite imaginative way and multiply it, taking care that sign does not change. And then we are applying some simple principle like taking limit. And and one profound principle was sandwich theorem, or say a squeeze play principle. So this tells you that such problems can be also tackled very easily if you have got basics in mind. Just try to note the motivation in each problem. Keep in mind, if there is no motivation, there is no solution. Okay, so let's go to some next one, some more challenging ones. So we'll have much to talk about it. So now I take up a problem, limit x tend to 0. It's little long, 1 over ln 1 plus x minus 1 over ln x plus root of 1 plus x squared. Now see, the first thing you see ln 1 plus x. Again, my remark that 1 plus t means you want this to be t. So what I will do, that I will write f of x as x, and g of x is x plus root 1 plus x squared minus 1. Why minus 1? Because x plus root 1 plus x squared tend to 1 as x tend to 0, but I want 1 plus, means I am writing now limit x tend to 0, 1 upon ln of 1 plus f minus 1 upon ln of 1 plus g. This is my expression. Note it very carefully. This f is just shorthand for f of x, perfectly legal. G is shorthand for g of x, perfectly legal. Now, I just want to simplify it. I know that ln of 1 plus f upon f is 1, because note f tend to 0. This was your choice of f. F x is f. So f tend to 0. And g was not this. G was x plus root x square plus 1 minus 1. So as x tend to 0, g tend to 0. So I can write this work as ln 1 plus g minus ln of 1 plus f upon ln 1 plus f times ln 1 plus g. The people who have done by different methods, they will of course have a lot of difficulty, even by expansion. What I'm offering you is very clean proof. So this is ln of, I just go about setting up my house in order. So ln 1 plus f over f, ln 1 plus g over g times fg, because it was not there. And ln, this is ln of a minus ln of b. So ln of a over b, 1 plus g by 1 plus f. So denominator is okay. Numerator, I will make some changes. I'll write ln of 1 plus, even 1 plus g upon 1 plus f, I want to write as something. So 1 plus g minus f upon 1 plus f whole upon fg, because this number, these two are already 1 and 1, so don't bother about them now. So the expression becomes this one, that limit x tend to 0, 1 plus g minus f upon 1 plus f. No need to carry g and f, they're very big expressions. Just in the final step, we'll put g and f. Now, as g tend to 0, f tend to 0, then g minus f also tend to 0. So this is like ln of 1 plus t, and t tend to 0. So I can further adjust it, and I can write this as ln of 1 plus g minus f 1 plus f upon g minus f upon 1 plus f times g minus f upon 1 plus f times 1 upon fg. In IT exam, you will take much less time to reach this, because you would not be doing all these things. You would be simply having your eyes fixed on what is to be done. And so quickly I can see through the game, and I will get this one, g minus f 1 1 plus f times 1 upon fg. Anyway, so this also becomes 1. This also becomes 1. Now, our final expression becomes limit x tend to 0. Let us see it, f g minus f. So G minus F upon 1 plus F times Fg. Now is the time to put the numbers. So your G was x plus root 1 plus x squared minus 1. F was x. 1 plus F was 1 plus F was still x. This is xf, and G is again the big thing, x plus root 1 plus x squared minus 1. Let me take you back to the beginning of the problem because it's a long one. You might have forgotten or not taken care of. This is limit 1 plus x and this one. So I wrote this as 1 plus f. This I wrote as 1 plus something, and that something is g. So this is my definition. Fx is x and gx is this. Because I want to use ln 1 plus t upon t. So ln 1 plus f upon f and ln 1 plus g upon g, I would be going after those expression or creating them. Similarly, ln 1 plus g, again I want to write this number as 1 plus something, and this should tend to 0. I am successful. So we are writing ln 1 plus g minus f. So ultimately this is what you get, g minus f. Now this last stage we have put these values. So now this is limit of x tend to 0. This x cancels. I'll write root 1 plus x square minus 1 upon x and times x plus root 1 plus x square minus 1. Don't worry about this one, 1 plus x. It has left you because x is 0, this one. Now, one last step. Observe that root 1 plus x square minus 1 can be written as 1 plus x square minus 1 upon root 1 plus x square plus 1. That's fine. We are using a minus b, and a plus b is a square minus b square. So it is x square about root 1 plus x square plus 1. The advantage of going from this expression to this is really good, that when x tend to 0, now this number does not go to 0. This goes to 2. That's non-zero. That's good. So x tend to 0, this tends to 0, but this tends to 2. So I will write now limit of x tend to 0, 1 over x separate. This number I will put here also and here also. So that is x square upon root of 1 plus x square plus 1, and upon x plus x square upon root 1 plus x square plus 1. Notice how I have played only with this part, not the whole. That would have spoiled the game. Now, once this is done, now we are almost okay. So that will be this one. This x gets cancelled. This is first not a problem. This becomes 2. This becomes 2. So that leave it. You have got x square upon x. You take out 1x from here. X 1 plus x upon root of 1 plus x square plus 1. Now this x square goes off. When you put x tend to 0, this becomes 0 upon 2. So this becomes 0, not 0 by 0. This becomes just 0. This is 1 plus 0. So you get here exactly 1. And here you have got 1 over 2. This 2 was down, 1 over 2. So your answer becomes 1 over 2 times 1. So your final answer becomes 1 over 2. So notice how we have written ln 1 plus as a final thing, comment that this is a long thing, but we cleverly or very shrewdly, we wrote fx as x. We chose f of x as x, or we chose f of x as x, and g of x we chose as it. I wanted to write it as 1 plus something. So natural choice was x plus root this minus 1. And moreover, as x tend to 0, both f and g, they tend to 0. So that ln 1 plus f upon f and ln of 1 plus g upon g, they don't have any problem. So, and then finally ln 1 plus f, and these all you escape, and quickly you go to the last step. That was you got g minus f upon 1 plus f and fg. Now is the time to see what f and g are, and when we calculate, then we simply get the answer, and it comes out to be 1 over 2. And it was just some kind of multiplying by conjugate, which I discussed, if you remember, in the first lecture itself. That's all for today, everyone. So let's meet tomorrow again. So that's all for today. Let's see tomorrow. And tomorrow, let's see what topic we connect.